Thank you so much, Brian. So good morning, everybody, and thank you so much for joining us today. As Brian said, you could be home, asleep, or playing computer games, and yet you're here to just learn and enjoy some physics and talk about Fermilab. And I'm here because you are here, because you showed this commitment, and because I want to see one day some of you be on this stage and be directors of Fermilab or any other laboratory. That's why I'm here today. So thank you for being here. And let me say in advance, congratulations on your graduation today. And let's get right to talk. I want to say, please interrupt me anytime to ask any questions, because I know when I'm listening to some talk and I don't understand something, then I cannot follow. I keep thinking about the thing I don't understand, and I lose track of the rest. So just interrupt and ask questions. This is meant to be just a joint adventure here. So today I decided I'd like to talk about Fermilab with you, about the science we do here, and about the aspirations we have for the future, and about the people we have, because we have amazing people. So we are America's particle physics and accelerator laboratory. And what particle physics does is, you know by now, of course, is to study the most fundamental constituents of matter, of our universe, and the interactions that bind them together and make the very complex and vast world that we live in around us, the entire universe. So particle physics studies the very beginning of the universe, vast as it is, with so millions light years across right now. Our universe began so small that it could be described by quantum mechanics. So we live in and the quantum nature of our universe, the quantum properties have left imprints throughout the universe that we live today. It is really an amazing story, and particle physics is the scientific discipline that tries to shed light and disentangle and answer some of the very fundamental questions. How did our universe evolve? How did it look like at the very beginning? How did it evolve to where it is today? So let's talk about some of the questions that we're trying to answer that are still unanswered. There are many unanswered questions, and we'll talk today about some of the tools we use to answer those questions. So we operate the largest particle accelerator complex in our country. Speaking of tools, particle accelerators is one of the tools particle physicists use to try to answer the questions. Telescopes is another, particle detectors is another, computational capabilities is another, and so on. So we operate the largest accelerator complex in our country, and second largest in the world after the Large Hadron Collider at CERN in Switzerland. We have about 2,100 employees, and we have a budget that's around $700 million a year and growing. It's going to get to close to $900 million in a couple of years. And this is because, as we'll talk in a little bit, we have a large number of construction projects that are going to bring online new experiments to study more questions. So we'll talk about all of this. So it is quite a substantial operation here, but the science and the discovery is what drives us. So we're sitting, as you know, on a beautiful 6,800 acres of federal land, and you can come in and walk on the trails and bike, and some of it is preserved prairie trails. And our facilities are used by many scientific users around the world, 4,000 or so, from all over the world. And those users some use accelerators, others detectors, computing, and so on. And as we move into the next 50 years, of our existence, our vision remains to solve the mysteries of matter, energy, space, and time, also for the benefit of all, because a lot of what we do and a lot of the technologies we develop have very practical applications for our everyday life. And this is a very important aspect. And by the way, one of the most important applications is what we're doing today, growing the next generation of our workforce, the next generation of scientists, engineers, technicians, and guiding them to go into STEM fields. This is an important part of our mission at Fermilab. So Fermilab was established in 1967 by Robert Wilson, from which a very visionary physicist, an architect, and a Renaissance man. He was the one who designed this beautiful, iconic building we're in today, the Wilson Hall. And so over the 50 years of discovery, we have in our past operated the Tevatron, which was the highest energy particle collider in the world at that time. That was before the Large Hadron Collider at CERN came about. And in fact, the Tevatron pointed to how the Large Hadron Collider, what the parameters should be and where to look for new particles and so on. And so the Tevatron was shut down in 2011 or 2012. And then after that, our laboratory decided that we were going to become the world-leading laboratory for the study of neutrinos. So we'll talk some more about that later. But in the meantime, during the history of our laboratory and using the Tevatron collider, we discovered the top and the bottom quarks, two of the elementary particles of the so-called standard model of particle physics. This is the grand theory that describes what we know about the universe today. So, and also the tau neutrino, and together with our partners at CERN, we contributed to the discovery of the Higgs boson, which took place at CERN in Geneva at the LHC in 2012. And today, the mission of our laboratory is really to execute the strategic plan that was described in the so-called P5 report. Let me take a minute to explain. The particle physics community in the US is very well organized. And of course, they have a very long vision. And every about 10 years, they get together and they come up with a particle physics project prioritization plan. That's P5, 5 Ps. So this is essentially a strategic plan and a roadmap for the direction of US particle physics over the next 10 years or so, with a 20-year horizon and in the global context. Now, imagine the one important point is that the instruments we use to do our research are very large and take a long time to conceive, to design, to execute, and then to operate. From the point, for example, a new experiment may be conceived to actually taking data can be 20 years or more. That's why this P5 strategic plan is a 10-year plan with 20-year horizon. And because those experiments are also complex, they require a very broad range of expertise and also a lot of resources, a lot of funding. Many of these experiments are done collaboratively, are global, is what I want to say. Multiple countries come together and work together on a certain experiment. For example, the Large Hadron Collider runs at CERN, and we are participants on that. We're users of that. We contributed to the accelerator, to the detectors, and now to the operation of the experiment, data analysis, and so on, because they are all several multi-billion dollars. By the same token, the neutrino experiment, Dune, that we'll talk about, that we're hosting we're doing here at Fermilab in South Dakota is also done as a global collaboration. So these are some of the very interesting elements. We're a very international community, and so the P5 report, that's why it's done in the global setting. So what we're doing now was executing the 2014 that identified 5 science drivers. One of them is the Higgs boson. As I said, in 2012, we discovered the Higgs boson at CERN, but now we need to study its properties, because understanding its properties, it's a very special elementary, we don't even know if it's elementary particle, a very special particle of the Standard Model. And we need to effectively have a Higgs factory to make lots of them and understand the properties of this tiny particle. And that's a whole thrust, let's say. Another is the neutrinos. Now, the neutrinos are elementary particles of the Standard Model. They are all over us, around us. They are ubiquitous, and yet we know very little about them. But we know that they played a very crucial role in how our universe, in how the world looks like the way it is today. And why do we know so little? Because they don't have any charge and they have very tiny mass, 1 million times smaller than the electron mass, which by itself is very small. And so therefore, with very small mass and no charge, they don't interact with matter at all. So so it's very hard to detect them as well. So neutrinos, but we know they played very important roles. So this is the second thrust. Dark matter is another. We know it exists, and yet we have not discovered it yet. And we know 96% of our universe is made of some form of dark matter. And yet we have not discovered it yet. So there are very important questions. Dark energy and inflation is another topic that has to do with how our universe started and evolved. And then exploring the unknown is maybe are there new forces, are there new particles, and so on. This is our current program, and I'll tell you, but I'm super excited to say that just last night I came back from Washington, where the new P5 report, the 2023 P5 report, was unveiled. And we were just discussing with Brian how thrilled we are with the strategic, the vision, and the roadmap that it lays out for the entire field, but for Fermilab in particular. So I don't have more to say now. It basically it pushes us to continue what we're doing, pushes us for an early implementation of our world-leading, world-class neutrino experiment, DUNE, that we're building right now, and even supports us to think long-term, a 20-year vision for our accelerator complex here at Fermilab, consistent with hosting a next-generation collider here at Fermilab in our laboratory, which could be a muon collider. Muons are other fundamental particles, just like electrons and so on. And so we're thrilled with the vision and with the priority that our program has in that report. I just want to tell you that it's a very important time in our field right now and for our laboratory. Okay, how do we do our work? We have a number of core capabilities. These are formally defined, and let me go through quickly because it's important to know what expertise all our people have. We have expertise in accelerators and detectors, both the science of them and the technology. We have expertise in computing, data, and computer science. We know how to run large-scale user facilities. This is our particle accelerator complex. And of course, we have expertise in particle physics. This particle physics is us. And as of recently, we were awarded by the Department of Energy that the core capability in mechanical design and engineering, and Mei Ling, who is sitting here, is our chief engineer, heading this effort, as well as systems engineering and integration. Very important for the work we do. And we have two emerging capabilities, one in microelectronics, very important for detectors, for all kinds of things, but also very relevant for our national competitiveness in chips production and so on around the world. So that has important societal applications. And also plasma and fusion energy and science, because we know how to build magnets, for example, for our accelerators that are also very important for fusion devices, for fusion research. So these are the main expertise that we have. And so let's go talk about our different scientific thrusts, and starting with neutrino science. So June, as I said, so maybe I should start by saying we have a number of ongoing neutrino experiments right now. We have a long-range neutrino experiment, and we have several short baseline, as they are called, neutrino detectors. We have 3 of those detectors here at Fermilab on our site, and one of them is going to start to operate for the first time in the new year, and we're all excited about that. Now, we're also building the next generation neutrino experiment, and this is DUNE, Deep Underground Neutrino Experiment. And we're building it to be the definitive experiment, neutrino experiment, to understand the mass ordering of neutrinos, as well as the so-called neutrino oscillations. It's going to be the best neutrino experiment in the world. How do we do that? We're building a particle accelerator that's called PIP2 here at Fermilab that's going to produce a very high power proton beam that will impinge on a target, and out of this interaction will produce the most intense beam of neutrinos is going to be generated. These neutrinos, because they interact so little, as I was telling you, almost not at all, they'll just, here is the neutrino production and the target. We'll first measure their properties in a detector here on our site at Fermilab, and these neutrinos then will just be directed to traverse the mantle of the Earth and travel 800 miles away, where they'll end up in South Dakota in an old gold mine, where we will be installing huge, immense detectors 1 mile underground in this mine. And the detectors have liquid argon, which is the next generation neutrino detector technology. And from the interaction of the neutrino beam with the liquid argon in the detectors, we're going to understand the physics that we're interested in. So DUNE is housed by the Long Baseline Neutrino Facility, or LBNF, which is a dual site at Fermilab and in South Dakota detector facility. It's long baseline because the neutrinos travel 800 miles. Why is that? Because neutrinos come in 3 flavors: electron, muon, and tau neutrino. And it turns out, as they traverse space and time, they change from one flavor to the other. And this is called neutrino oscillations. And so you can generate, for example, here at Fermilab, an electron neutrino, but then that same neutrino, when you detect it in South Dakota, is a tau neutrino. And the distance between Fermilab and South Dakota is roughly 2 complete oscillations. And from the properties of these neutrino oscillations, the rate at which they occur and so on, we believe understanding that is related to why the universe is made of matter rather than antimatter. Very fundamental question. If the universe, whereas at the very beginning, equal amounts of matter and antimatter were produced. But now we know the universe is made of matter. If not, we would not be here because matter and antimatter would annihilate each other. So these neutrino oscillations is what we're after with the Dune experiment, and this is geared towards answering this very fundamental question: why our universe is made of matter. And we're in the middle of building this. I'll tell you, LBNF is the facility. So when LBNF and PIP2 the accelerator and Dune is the experiment are all done, we definitely think US will be universally acknowledged as the world leader in neutrino science for decades to come. And this is our highest priority. So what are the science objectives of Dune? And by the way, the LBNF is a $3 billion project. PIP2 is roughly $1 billion project. And Dune, which is done by an international collaboration, is also in the billions. So this is a major investment, both by the US, by the Department of Energy, but also around the world, funding agencies around the world, which is commensurate to the importance of the science that we try to unravel here. So we talked about the origin of matter as one of the major scientific objectives of Dune. Another one is the ability to look into the cosmos and watch the formation of neutron stars and black holes in real time. And another one is the unification of forces. So we believe that ultimately all four interactions, the distinct interactions, should be converging into one, if you like. And this was Einstein's dream, in fact. And understanding, and Dune is going to help us shed light into this hypothesis. Effectively, to realize Einstein's dream of a unified theory of matter. So Dune, as you see, will be able to address many fundamental questions, not only in neutrino physics, but in particle physics as a whole, and in science for that matter. So this is a picture of what's happening in South Dakota, 1 mile underground. The caverns were excavating 3 huge caverns in order to install the detectors with the liquid argon. So the north and the south caverns are the ones that will house the detectors. Ultimately 3 detectors. Phase 1 that we're executing now is going to be 2, 1 in north, 1 in south. The middle is a utility cavern that houses cryogenics, electronics, and so on. Note the dimensions of these caverns. So each one of them is about 150 to 180 meters long, 20 meters wide, all of them, and between 30 and 11 meters in height. So these are huge. And to excavate, we need to excavate from a mile underground to make these caverns. And that means we need to remove 800,000 tons of rock and bring them to the surface and get rid of it to make room for the caverns. Well, it turns out that this excavation is 92% complete, and the central utility cavern and the north cavern are totally complete in excavation. And this is a picture of the north cavern, and you can see a man here just to give you a sense of the scale we're talking about. We're doing something almost impossible here, and we're succeeding. And this is another picture from the north cavern that was more as of August of this year. And this is a photograph from the central utility cavern where the excavation is complete and the concrete slab is mostly in place. So excavation is going very well. And as I said, DUNE is an international collaboration of 1,400 scientists and engineers from about 200 institutions, 50% US, 50% from around the world, and lots of students and postdocs. And this is from their collaboration meeting they had last May here at Fermilab. Very nice. And we will be the host lab for the DUNE collaboration. So when the physics starts, which is in 2028, it's around the corner, not very far. By the way, we're starting to install detectors in the caverns next year already. So it's very exciting. And the detectors are made by partners from around the world, CERN and France and UK and so on. So they'll all bring their detectors to install them in South Dakota. So, so we are the host of the DUNE collaboration. So when physics starts in 2028, we're going to have here to welcome, let's say, scientists from around the world who come to do science with the DUNE experiment. And we already have established an office dedicated to prepare our laboratory to be responsible hosts for the DUNE collaboration. So those are the time scales we're talking about. And a couple of words about PIP2. That's also very dear to my heart because I used to be the project director of PIP2 before I became laboratory director. So PIP2 is an essential upgrade to our accelerator complex to allow us to get to more than 1 megawatt of proton beam power, 1.2 megawatts initially, ultimately above 2 megawatts beam power in order to produce as many neutrinos as possible, but also in order to produce a broad physics research program for decades to come. So we're building PIP2, this accelerator, based on superconducting radio frequency technology. That allows us to run more beam than DUNE needs. And then the idea would be to do some tricks and be able to point the extra bunches, if you like, to other directions, to other experimental destinations. So our dream is to be able to do multiple experiments using PIP2 in parallel, simultaneously with DUNE. And that's how we're building this accelerator. And this is the cryogenic plant building, which is completed. Construction has started of the PIP2 accelerator. We had a groundbreaking last April with the Undersecretary of Energy, Governor Pritzker, and Congressman Foster, and so on. And we're building these so-called cryomodules. These are accelerating units that 10 meters long, in collaboration also with international partners. PIP2 is also an international project, and in fact, the very first project, accelerator project of the Department of Energy that's done in collaboration with international partners. In fact, the partners are delivering about $300 million in-kind contributions to PIP2. So imagine this, that's how our field works. So other people in other countries UK is going to build 3 of those and ship them here and will install them in the PIP2 accelerator. And France is going to build another type, 10 of another type of cryomodules, and so on. So other countries are building equipment, that's scientific equipment, that's installed in our own country here, in our backyard, in your backyard, all of ours. Okay. This is a nice picture I find of PIP2, that the cryoplant building that I liked in the dusk. And that's another cryomodule that we built, the very first one. It has 5 different types of cryomodules, and the team around, very proud team of technicians, engineers, and scientists who built the cryomodule. Mei-Ling, are you here? Maybe not in this picture. Okay, but some of Mei-Ling's people are here. And this is the high beta 650, different type. Now, let's move on to collider science now. This is another thrust, to study the Higgs boson. Okay, so the collider science is done at CERN, in the Large Hadron Collider, not here. And the Large Hadron Collider, as you know, is 27 kilometers in diameter. It is in Geneva, Switzerland, and it is also a very excellent pioneering machine that collides protons with protons. And the idea is to, first of all, the Higgs boson was discovered in 2012 by this accelerator, this collider, and now it is being used to understand the properties of the Higgs boson, and it is also being upgraded to a higher energy and higher power. And Fermilab and US contributes to the upgrade of the accelerator and of the detector, one of the two major detectors, the CMS detector. And Fermilab, in fact, is the host lab of the US CMS collaboration, just like Dune. The CMS detector has a whole collaboration around it, which is, by the way, about 3,000 people. And the US contingent of that is around 1,000 people, and Fermilab is the host lab of the US CMS collaboration. And we have, in fact, ROC East, a control room, remote operations center, where anyone from the collaboration can come and take shifts on the LHC as if they were at CERN, in the control room at CERN. So that is part of our service that we provide to the US community. And CERN is our very special partner, is our European sister laboratory. And as I said, we're first of all, we participate in the operation of CMS, the experiment, analyze data, ROC is used to take shifts, and we participate and lead the high luminosity LHC accelerator upgrade and the CMS detector upgrade. Those are two distinct projects. And maybe I can give you a sense. This is another cryoassembly that was built here at our laboratory. This contains two final focus magnets of the high luminosity LHC upgrade. We built the whole thing here, and in fact, recently it was shipped to CERN, and on the 18th of December, it arrived very safely, are going to have a big party to celebrate. That is the very first deliverable from the US to the high luminosity LHC project. And so we're building cryo modules, we're building cryo assemblies with magnets, all kinds of things. And this is a picture when it was ready to be shipped to CERN. And this is the PIP2 cryo module I showed you that's going to be shipped to the UK as part of the transportation test we do. It's going to go on an aeroplane, and the 10-meter huge cryo module, and it will arrive there, be tested, and then sent back here to make sure the transportation won't damage any of its properties. And this is our Office of Science Deputy Director signing the cryo assembly. Okay, and I call it the power of the international collaboration. Now, I told you that we're very good at producing very high power proton beams, and we're also very good at high power target technology, and we impinge protons on targets to make neutrinos. Well, when you do that, you also make other particles. Among them are muons, also elementary particles. They are the cousins of the electrons, the heavier cousins of the electrons. So we produce muons, and we use them to also probe parts of the standard model. We know already the standard model of particle physics is incomplete. We know that. And so by doing experiments with muons, we try to understand where is the missing physics, basically. And one of the experiments we just finished recently is the muon G-2. We took data, we completed, we achieved our statistics goal, and in fact, in this past August, we published the most precise measurement of the muon anomalous magnetic moment. And the data set is shown here. And we still have more data to analyze. And now it is a showdown between experiment and theory. The two don't quite agree. And in the next couple of years, we'll keep analyzing the data. We'll also advance the theoretical model, and we'll find out in the end where we are. If there is still discrepancy at the end of this, it will be a hint for new physics, and it's going to be very, very exciting. So this is one thrust, and another is a muon to electron conversion project. This is under construction now. I should have added one of these solenoids yesterday was installed into the experimental hall for the very first time to its final location. So this is a project to study the conversion of a muon to an electron, never observed before. If we observe it with this experiment, which is roughly $250 million, if we observe it, it's going to be huge, very new physics again, first time it will be observed. So this is going to be done, we're building it, will be done in a couple of years, and we'll take the first data 2026. And we're making good progress. And then, of course, we also study the cosmos, because as I told you, they are all related together. And for that, we use telescopes. Some of them are in Antarctica and some in in Chile and in other countries. And we also use small experiments in the laboratory to try to discover and understand the nature of dark matter. And we're experts in accelerators, both science and technology, in the physics of accelerators, in superconducting radio frequency technology, which accelerates particles to higher energies, and it is the preferred technology for all modern accelerators, and we're world-leading experts in that area. We're experts in high-field magnets. Remember, for the high luminosity upgrade of the LHC, we made the cryo-assembly. We're great experts on that, as well as high-power targetry. And our expertise, in fact, are used by DOE Office of Science to help with other programs. For example, I don't have that. For example, we help build cryomodules for an X-ray laser out at Stanford in California. And we're building magnets for a neutron source in Tennessee, SNS, and so on, which is very nice. We are the partner of choice for accelerator things. And our accelerator complex has multiple different destinations, targets, test facilities, and so on. And recently we achieved a new record in proton beam power, which is 960 kilowatts, almost a megawatt. So we're doing very well. And this is a list of all the construction projects that we are executing simultaneously right now and how far out they go. So I'm very delighted that I can start putting some check marks on some of them. And I'll show you a picture of the IRC building. You see LBNF and Dune, 3.3 billion. You see PIP2, roughly $1 billion. You see the high Lumi LHC accelerator and CMS. You see the mu2E and so on. And this is an infrastructure project. And we're doing very, very well in the execution of these projects. I would say over the past year, we achieved 10 formal approvals by the Department of Energy. It's roughly one every month. So it's quite extraordinary. So we're sitting on a $5.5 billion portfolio of projects that we're executing, if you sum all of these up, and an additional billion or so from in-kind contributions from international partners. So not easy. This is a beautiful picture of the Integrated Engineering Research Center of IRC. You've seen it as you come into the Wilson Hall. That was completed recently, executed truly with excellence, and it also received the project award. Not only is a beautiful building, it's sustainable, and it's going to unite all our engineers, or the majority of them, in that one area. And we have a proposal to rename it after Helen Edwards, to rename that building to Helen Edwards Engineering Research Center. And Helen Edwards was the designer and builder of the Tevatron. And she does not live anymore. She was an amazing scientist and head of the accelerator division here when I was a graduate student, actually. So I would walk in front of the control room every night to go to my office and work, and she was always in the control room watching and overseeing the commissioning of the Tevatron. And so I'm truly delighted that we have, there is a legislation in place to rename this after her. And I particularly love the quote by Senator Tammy Duckworth, who said, not only is renaming the IRC after her well-deserved, I think it tells generations of girls interested in science that they belong at the table. And with all the expertise that we have, we also use and advance 3 of the national technology initiatives. And these are quantum information science, artificial intelligence, and microelectronics. And I don't want to go through, how am I doing time-wise? What time is it? Okay, so I don't want to go through all the details. I just want to say that this SQMS is center studies quantum science and technology. It is one of just 5 DOE national quantum information centers. And so, and it has many partners. It's thriving. The center, the idea is that it brings together academic institutions, universities, industry, and national laboratories. Because all of these are essential to create the ecosystem necessary to advance quantum sensors, quantum computing, and so on. And this, our SQMS center, in fact, is utilizing the same capabilities that we use to build very high efficiency superconducting accelerators to build long coherence quantum computers. That is the main idea. So it is really brilliant, and it attracts a lot of the young people as well. So you can see some of the partners here, and now we're also collaborating with international partners. And recently we inaugurated the so-called quantum garage that has a number of these dilution refrigerators. It has 5 of them, and then people from anywhere in the country can really come and bring their qubits or their algorithms and so on and do experiments. The idea here is that we start to have a user test facility that users outside Fermilab can use for the research. And again, you can see Pritzker, who loves us, and Martin Torres is his deputy, and Foster, and so on. And it was a very nice event. And I want to take a minute to talk to you about another vision we have for Fermilab and our communities. And we call that Discovery on the Prairie. And this is the following. So the state of Illinois has appropriated $30 million for Fermilab to build a new housing facility for our users and other communities. And around that, we want to develop a broader vision, and we want to tie this with our STEM programs and with our community outreach and with even to a tech hub to, to try to tie this new housing facility with a place where industrial partners can come and work in close proximity with our scientists and engineers and accelerate the transfer of the technology innovation into the industry effectively. And so we are in the process of developing, in addition, a vision for our village. Our village is where users and other affiliates stay. So we're developing a long-range vision for our village. Part of it is the first phase of it will come from the 30 million installment from the state, but it's a lot broader. And we tie it, as I said, to amenities and so on, to a welcome center, to STEM education and outreach, and a technology hub. And we have established a steering committee. We're engaging our user community, and when we would like to also invite you. We want to let you know about it, because when we put it in place, it's going to be a place for our neighboring communities as well to take advantage of it. And I'm also very proud to say that this past summer we hosted 316 interns here at Fermilab. And so that's something for all of you. When you go to college, you know Fermilab is a place you can come back to and work in the summer. By the way, you can work not only on scientific things, but also on engineering, but also on laboratory administration and operations aspects, with finance people, with even our legal department and so on. We have interns across the board. And this past summer cohort was the highest we had in the 44 years of history in pipeline programs in our laboratory. The Wilson Hall was buzzing with noises and so on from so many kids around. It was great. And last, I want to say sustainability is a concept that we take very seriously. We have a new sustainability team, 4 FTEs working on it. We're developing a strategic plan for sustainability. We apply it not only to buildings, but also to accelerators, to our scientific infrastructure. It is the right thing to do, to start from the beginning when you design something new, to make sure that it runs in an energy efficient way. Each component is designed with energy efficiency in mind, that we recycle the energy, and that we use green sources of energy as well. So all of the above. And this is a responsibility we have to our society to do this. And I want to close by just saying to this cohort of the Saturday Morning Physics students that my advice, let's say, to you is just follow your passion and do what you really love to do. Decide what that is, and go for it and do it, and do the best job you can about it, and try to make a difference. Try to leave something. That's how I think about my job. My job is to leave something behind me that the next generations can use to do their science or to do technology innovation. And above all, have fun. As I say, we got into physics for the fun of it. So thank you very much. I think the end was a little abrupt, but that's okay.
Hey everybody. So
Questions?
I hope you enjoyed that overview of what we do and why we do it and how we do it. This was sort of low-key kind of a business end of S&P. We want to encourage you to really join us, and we wanted you to know what you were getting into. As you can see, not only do we do pretty great science, but we have a lot of support to do it. So if you come join us, it's likely you will somehow get entangled with. With that being said, are there any pressing questions? Want to know anything?
I was wondering how Fermilab is leveraging generative AI technologies in their work. So if you could maybe talk a little bit about that.
Which technologies?
Generative AI, knowledge production and other things,
Ah.
like ChatGPT and other things.
I would say we are leveraging AI technology. I don't know about ChatGPT so much, but we're leveraging AI on multiple fronts, both on for the experiments and for the accelerators. For the experiments, for example, we have a vast amount of experimental data coming in to the detectors. So we use already AI to sort out and guide us as to the subset of all of this data that contain the useful information. By the same token, on the accelerator side, we use AI to allow us to come up with algorithms that can help us, let's say, tune the particle beams to the desirable parameters, and to do that in a robust and repeated way and a uniform way, and with a minimum let's say, interference of humans, and in the fast possible time, as speedy as possible. So let me just go back to this slide. Give me a second. I think this is a very good question, and I skipped that here. Okay, let's see. First of all, we have unique challenges in HCP, and we believe AI can ultimately transform HCP. But also, the advances that we bring also help with societal applications of AI and industry and so on. So, and there is synergy between AI and microelectronics. So AI-enabled automation and optimization. Let me give you another idea. When we designed the Dune beam line, and then we applied machine learning algorithms to the design, we ended up gaining about 30 to 40% more effective yield out of the neutrinos than before using machine learning. So you see, by using only software, if we were to do that with instrumentation, with equipment, with hardware, it would be very costly. So by using only software, we increased the yield of the neutrino yield tremendously, and that amounts to more statistics for our experiment, is what I'm saying. This is an example of optimization. Experiment design, as I was telling you, the detectors and so on, readout and control, data processing and simulation, and data mining, analysis, and interpretation. So on all these fronts.
So specifically about generative stuff, it's a bit too complicated for us to apply to exactly what we're doing. The GPT is a general purpose transformer, right? So you're training it on everything, and we don't need to train on everything to look at.
Thank you, Brian. Yes,
Yeah.
Thank you.
So we use simpler models because they're less expensive to train. We got.
I think we want the students
Hello.
to ask questions too, not only the not only the
I'm just curious why
Of course.
Why the Dune projects got to go underground, and could you do it like in the ocean or in space or something like that too, or does it? What's the reason that it has to go through the Earth?
Fantastic, excellent question.
Thank you.
So first of all, the reason it has to go so much underground is that it's shielded by neutrinos coming from the cosmos and other types of radiations, events, and so on. It turns out there are neutrino detectors that are in water, and in fact, also under ice. There are all these different experiments. There is a neutrino experiment off of the coast of Greece, in fact, that I saw recently, the detectors they are making. This is under the Mediterranean Sea, some, I don't know, hundreds of meters from the surface. And then IceCube is a neutrino experiment deep under the ice. So it's a telescope in the ice for neutrinos, effectively, from neutrinos that come from the cosmos. So there are all kinds of different variations of that. But the reason for us is that we have as clean a signal as possible, because what we're looking is a needle in the haystack, basically. It's very difficult. Because neutrinos don't interact so much, the events are very few. To make them as many as possible and increase the statistics, which will yield the new physics, we maximize the neutrino flux. We have the most intense beam of neutrinos, hence the most intense proton beam. We maximize the volume of the detectors. That's why each detector is so huge. And we maximize the time during which they run. So it's the megawatts, the kilotons, and the years is the figure of merit.
For the Dune project, you were talking about you were sending neutrinos from this lab to the South Dakota lab, and you also said that neutrinos can be tau or they can be the electro version. So could you technically send messages like in binary if you learned how to, like how they change between that distance?
Actually, you could, right? Can somebody help? In fact, I think I maybe can. Brian, please.
You need a mic, or you need an assist? Oh, so it's actually something I'm working on.
Oh, thank you, Brian.
What you need is you need to significantly enhance the cross sections at which you can see neutrinos. The reason you can shoot them through the Earth at South Dakota and they get there is because neutrinos don't really interact with anything, more or less matter phobic. So the critical challenge there is creating something that will actually allow you to see neutrinos more efficiently. It's something that I'm in the process of developing, although I don't know if I'll go forward with it, because if you can see neutrinos, you can see all the nuclear reactors in the world, and that reactors from submarines that might destabilize. It literally might destabilize nuclear deterrence. But it's something I thought about and put active work into doing. Yes, you can.
I have the feeling I heard there is an experiment or something, even outside, about using neutrinos to transmit messages. There is something else out there.
Yeah, so there are conventional experiments that have tried it, but the cross sections are incredibly low.
Low, okay,
Yeah.
okay.
So there have been some Wall Street companies that have tried to do it.
I see,
Yeah.
okay. Thank you, Brian.
No
Thank
problem.
you. Yes.
I got a quick follow-up. So you can know exactly which type of the three of the neutrinos is it that you produced? If yes, measuring going to create quantum interference, like your measurement as it leaves. I saw you had the measurement. Isn't it going to, I don't know, will collapse and determine? Are you going to stipulate? Okay, this is going to the type now, and when it arrives, no. How do you know which ones? You're probably creating huge, vast volumes of the same particles, right? And they go through your measurements, so you start. When it arrives in the mine, how do you know which one is it that you created? It didn't change when you measured it, and which one it is exactly that it arrived. Number one. Number two, regarding your trickling of technology to the industry and the quantum garage. Is the program going to be open to, I don't know, utilities and companies like that to leverage some of the quantum capabilities you guys are developing?
I believe the answer to the second question is yes. We already, as you saw, work with a broad range of companies, of industry. In fact, IBM recently expressed huge interest. We're working with Rigetti. So, and I think there is, let's say, we're being encouraged both by the federal sector and by the state to work with the industry and jointly to develop technology together. So I think utilities is absolutely. We're not the ones who do the technology transfer exactly. We're developing, we're in the low TRL levels. So on your first question, I'm going to need some help. But we do know exactly which neutrinos, we tag them sort of, right? So we know a tau neutrino, whether it converts to an electron or something. Is that correct? Can you? Yes.
Oh, yeah.
Thank you.
All right, let me just introduce myself. I'm Eric James. I'm a scientist here at the laboratory. I work on Dune, and my son happens to be a senior also, so that's why we're here today. So, you know, the way that Dune works is that when here at the laboratory, we actually produce muon neutrinos. So most of the neutrinos that get shot out towards South Dakota are actually muon neutrinos. And then as they travel through the Earth, they actually exist in sort of what I would say is an ambiguous state. So as they move out, they're not actually one type of neutrino or the other. They're actually a quantum mechanical state, which is a combination of all the different types of neutrinos. And you only know the only way that it actually becomes a different type of neutrino is when it interacts in your detector. So it actually, you know, it's in this indistinguishable quantum state until it actually interacts with other particles in the detector, and then it becomes the other type of neutrino at that point. So it's a little bit complicated in that respect, but you know, essentially what happens is as it travels around, it's different parts of the different neutrinos, and then the way you can think of it is that, you know, as you travel a certain distance, how it's mostly an electron instead of, you know, originally mostly a muon neutrino has some probability for interacting both of those types. So it's a little bit, you know, we usually talk about it in sort of a simplistic way, actually a little bit more complicated.
Thank you so much, Eric.
Yep, no problem.
For shedding light and clarifying.
Sure.
Yeah.
So I would say a simple way of explaining it is that the universe, reality treats neutrinos like prisms treat light. There are different frequencies of light, and if you shine it through a prism, you can see the rainbow. Reality does the same thing with neutrinos. That implies is that neutrinos are in a quantum superposition state. It's long-distance quantum superposition. What's the next question?
For a kid, student first. And,
about neutrinos, what's the actual difference in interaction between the three flavors? Like, is it something to do with spin or mass or energy, or what's the actual difference?
Okay, Brian, go ahead.
So I'm also a neutrino physicist. I'm a scientist. I also work on Dune. So what you have is that superneutrinos, as they travel in a flavor state. So whether they are an electron, muon, or tau neutrino, there's actually a quantum superposition of mass states. It is that they are different energies. They're combinations of those different energies. And the reality treats those different energies differently as they travel through space and time. You're really looking at our different combinations of contributions of energy into our reality. Way of thinking about it. When you take a picture of it with a detector, you're essentially catching it at a snapshot as those energies interact with each other as they move through space and time. Because it's a probabilistic effect, you can essentially roll the dice and say, am I going to see a tau or a muon, just like am I going to see a snake eyes or a 12 on like that.
We can also say the masses are different, though, among the three
The
neutrinos.
masses are different.
And in fact, we don't even know how they are ordered. And this is one of the fundamental questions that the Dune experiment we're building now is going to nail definitively with 5 sigma, the ordering of the masses of neutrinos. So that's one difference.
Yeah, I have a follow-up question. Okay, so if the difference is in mass, and does it only go from like a higher mass to a lower mass state, or like where does the extra mass go?
A good question, Brian.
It doesn't. You can go from a higher mass to a lower mass state. It's that the actual neutrino, as projected into flavor space, the space that we see, has contributions from all of these mass states. Add enough energy to the whole system relativistically by accelerating it, you access these higher mass states that aren't necessarily present in the neutrino you out into the universe. Does that make sense? So basically, if you run really fast, you like get a lot of extra energy, and that can turn into mass sometimes.
Yeah.
On here.
What are the implications of like the results of the Dune experiment? So like if you find that a certain number change into a certain flavor, what does that mean for physics?
We'll talk on this. Do you want to take this one, or you want me to? No? So the way I think about it is that neutrinos encode some answer about the difference between matter and antimatter, or at least a model of how that could work. So we're at this particular energy level in space. What this essentially says is there's a difference between what it means to be us and what it means to be the anti of us. And that is taken into account when you think about it quantum mechanically. You would have to do to apply that to what's going on with the Big Bang and explain why we're here, as opposed to why antimatter isn't here, or why we haven't annihilated and we're just nothing. You'd have to evolve these equations up to a higher energy state. So essentially what we're doing is we're getting a proof of concept, or sort of a model of how we can explain why we're here.
Won't Dune also help? So the neutrino masses are an unknown quantity, and even like whether, it's M1, M2, M3, they're unknown quantities that they're trying to measure, and the ordering of the masses is one thing that Dune will also help illuminate. Here.
All right, we got a lot of questions coming. What's going on, guys? This is supposed to be the talk where you learn about what you can do. The previous 10 talks, we were supposed to talk about all this stuff. So if you really want to learn, we're going to take a few more. If you really want to learn about this stuff, come work with us. So
Yeah, that's the best answer.
So we could talk about it 8 hours a day if you really want to. We'll take a couple more. Go ahead.
So since you've been talking about the different kinds of neutrinos as like being in a quantum mechanical state, is there a way that we're using quantum computing to be able to look at that from its like without disrupting the system as much as we are, or are we still using like classical computation?
So we're developing quantum computers. They're not quite at the state where we can use them for those sorts of calculations yet, although somebody who you saw talk, Gabe Perdue, tried to calculate neutrino cross-sections using a quantum computer. He ran into some issues, but I don't know, maybe you guys should email Gabe and see what's going on with him, ask him those questions. If you want quantum computers to be able to do stuff with neutrinos, work with us and figure out how to make it happen, because we don't know yet. We haven't figured it out yet.
But
So
we're headed in that direction.
we really are.
We want to get to the point where we use quantum computers to calculate.
All right, we'll take two more, and then we gotta go get coffee. All right.
So if a neutrino was to like change, to like a higher mass state, would it like lose speed?
So here's the problem, right? You're not really dealing, when you talk about a neutrino as a particle and it like you think of it as a ball, but it's really, it's a collection of wave packets. And I know that's hard to think about. So it's not that it slows down.
It's energy. We should
It's
talk in
it's
terms of energy
Yeah,
instead of speed
yeah.
for these particles.
I think the group velocity, the what you would call the speed for those packets. I think I don't know. I have to really sit down and do some calculations. Yeah, I don't know. What do you think? It's true, but so right before it interacts, do you think something has to happen where it's interacting? All the way state, all the mass states interact at the same time. Would you say that if it transformed into a tau, would the speed at which it interacts be less than when it was made? I think what I want to say is yes, but the problem is I haven't done the calculations to look at the group velocity of the wave path. I don't know. What do you think?
Exactly. In this regime, we talk about energy rather than speed or velocity
So
because it's so close to relativistic. It's so close to the speed of light.
so the general consensus is when we do our calculations, we don't see the effect. However, there is probably an effect. And to tell you a definitive yes or no in the way that you're asking, we'd have to do the calculation. Probably yes.
So I have some questions regarding like the actual setup of the experiment. First of all, does Fermilab create their own neutrinos of the different flavors, or do we use ones that are already like in the world? And once they're sent to South Dakota, what do you do with the neutrinos there?
Eric, thank you.
So first of all, I guess the first part of the question is the creation of the neutrinos. So we do create our own neutrinos. That's what the accelerator does. So the way that the neutrinos are created is we actually start with protons that we accelerate in our accelerator complex, and then we basically smash them into like a target, which is essentially like smashing them into a ball. And when that happens, a bunch of different stuff pops out because of the fact that the protons are interacting with the particles in the target. And one of the things that pops out are these particles called pions, which are a certain type of particle, and then these pions pop out the other side of the wall, and then they travel down what we call a decay pipe. And while they go down that decay pipe, they will decay into a muon and a muon neutrino. So we actually create those muon neutrinos, and then that's what's passed through the Earth to the laboratory in South Dakota. So that was the first part of the question. And the second part of the question, remind me what that was. It was how do we detect them when they get to South Dakota? Okay, so so these neutrinos are like passing through 800 miles of solid rock as they get to South Dakota, right? And we have these huge detectors there, but almost all the time what happens is the neutrinos just pass through our detectors and nothing happens at all, right? So that's why Leah was telling you that we have to make these incredibly powerful beams because we have to send billions of neutrinos through the Earth just to see a couple interact with material inside of our detector, right? So every once in a while, so we're sending these billions and billions of neutrinos through the Earth every day, and maybe let's say 20 times a day, one of them will happen to interact with the liquid argon in our detector, and then the neutrino will interact with one of those liquid argon atoms, and it will produce some charged particles that then we can actually measure in our detector and see what type of neutrino it was. So the type of interaction that we see in our detector will be different if it's an electron neutrino or a muon neutrino or a tau neutrino. And then essentially we can just count how many of each one that there are, And, you know, we know that we're sending mostly muon neutrinos from Fermilab, so by that we can see how many have changed and what we're expecting in that pattern when we get to South Dakota. Your question, or?
Yeah, just one quick follow-up question. Can we anticipate any changes by sending so many neutrinos like under the surface of the Earth, like maybe to our daily life or like the makeup of the planet, or are neutrinos non-reactive enough that they won't play a difference?
Oh no, I mean, you know, it's not. I mean, from a knowledge standpoint, we're obviously learning things, but they're not going to have any impact on the environment or the surroundings. I mean, the sun produces an incredible number of neutrinos that are streaming down all the time and passing through us. So, I mean, I can't remember. I should probably be a little bit careful, but you know, essentially, you have like, you know, 1 billion neutrinos from the sun passing through your body every second. So, you know, there's just a huge number of particles, you know, neutrinos passing through us all the time. And, you know, the statistics are is less than 1 of those neutrinos will interact with your body over the course of your lifetime. So, you know, even though you have billions passing through you every second, only 1 over the entire course of your lifetime will actually interact with like a cell inside your body. So, you know, these extra few neutrinos that we produce and shoot through the Earth are consequential compared to the number that actually exist in the universe and are, you know, passing through us all the time.
Thank you, Eric.
Yep. I think the funniest thing is that because the neutrinos don't touch anything, we're essentially shooting a bunch into space. The planet spins, so neutrinos are doing this, right? And we're just orbiting around, so we're like a pretty bright neutrino object, but also the universe is fairly bright. So that was the last question. Anything else you want to say?
Thank you all so much. Congratulations again to the graduates, and come back and work with us when you go into college and so on. Best of luck. We hope to see all of you again at a future time. Thank you. Thank you.
Hey, can y'all hear me? Yeah, so this is why we asked you to sit as close as possible, because now we're going to do the graduation portion, which is going to celebrate the students who managed to make it through our rigorous semester of learning about modern physics. So the way this is going to work, let's see. One of us is going to read names. One of us is going to shake your hand and switch off per slide. So it would probably be a good idea for people to line up here when we call you, come up, the handshake, and go that way. Sound good? All right. So let's see. Over this year, we had 117 students participate throughout the session. 100 students earned a certificate of accomplishment, which is fairly good for what we usually do. We typically get about 75 to 80 per year. And 56 students also got perfect attendance, which is somewhat below, if that's okay. So now we will begin with the announcement of the names. So read it. Okay.
So apologies if I butcher names. It's gonna happen. I'll do my best. So going in alphabetical order, so you might be able to anticipate when you're up next. First we have Ayush Adi. Hope I did all right. Is Ayush here or on Zoom? Not sure.
And then read what they got, certificate of accomplishment.
So certificate of accomplishment as well as perfect attendance. So this says this acknowledges that you successfully completed the 10-week course in high energy physics conducted by the scientific staff at Fermi National Accelerator Laboratory, and it has our signatures on it.
Apparently, Ayush is in the bathroom.
Oh.
So should we wait? Maybe we'll run up and grab him. Be right back. So are you sure he's in the bathroom? Why don't you go grab him?
Yeah.
Oh, different Ayush? So is Ayush on Zoom? Oh, there's a chat coming up. What's going on? I'm sorry this is so disorganized, y'all.
Ayush is on Zoom.
Ayush is on Zoom. Okay.
So people on Zoom, your certificates will be mailed to you. I found out. So fret not, you'll find a way to get this certificate. So next we have Vivan Agarwal. Vivan here, did I say that all right? Certificate of accomplishment. No?
Okay, I don't see Vivan.
All right. Next we have Malaika Ali, certificate of accomplishment and perfect attendance. Malaika. Right. Next we have Ibrahim Anwar, perfect attendance.
What's going on, bud?
William Arasan.
Okay.
Certificate of accomplishment and perfect attendance.
Probably on Zoom.
Probably on Zoom.
Hope you did your clapping exercises, because we're going to do a lot of clapping.
Akshara Arvind. Certificate of accomplishment.
Hurrah. Thank you. Does anybody want pictures or anything? I guess not. It's okay. Well, where's your mom? Your mom should be closer. Oh, okay.
Sanjit Jyoti Bala. Yes.
You got to read off what he did.
Certificate of accomplishment and perfect attendance.
Good job,
Good
Sanjit.
job.
All right, I'll take it. Oh yeah.
I'll take.
This is so different. Thank you so much. Yeah, thank you.
Reminds me of my graduation.
Hey.
Well, not, just calling the names. It's been a while.
As long as you got the paper, right?
Yeah.
All right, next we have Oriana Berdnikova, and the certificate of accomplishment and perfect attendance. Hey.
Good.
Syed Mohammed Abdullah bin Hassan, certificate of accomplishment. Anyone?
Good.
Oh. Artarva Berduta, certificate of, I'm sorry, that's perfect attendance. Good job, bro.
That's picture. Yeah, thank you.
Next is Kyle Bledsoe, certificate of accomplishment. Next is Sai Sanjay Bomisetti, certificate of accomplishment. Here you go. Thomas Boss, perfect attendance. No, right? All right, you want to switch off or you want to keep them going? Okay.
All right. Daniel Mo Brookins, certificate of accomplishment and perfect attendance.
Mosiah. Where at least says Mo? Is your father going to take a picture? Yeah, of course. Come on. You want one more?
Cooper Brown, Certificate of Accomplishment. Cooper here.
I don't see Cooper.
All right. Caitlin Carey, Certificate of Accomplishment. Rashawn Carter, Certificate of Accomplishment.
Yeah, bud.
Shihan Chang, Certificate of Accomplishment. Shihan here.
I don't see Shihan.
Sophia Contreras, Certificate of Accomplishment and Perfect Attendance.
Good job. Pictures?
Want me to keep going?
Yeah, let's swap. Davina Das.
I don't see.
Certificate of Accomplishment. However, Davina.
Oh, it's under.
Is it under? No.
Somehow the.
That's weird.
We
got out of order.
The slides are out of order.
Okay. Here you go.
Here we go. Congratulations.
Harrison Delighten Brugman. Certificate of Accomplishment and Perfect Attendance. Sophia Daly, Certificate of Accomplishment and Perfect Attendance. Isaac Del Moro, Certificate of Accomplishment and Perfect Attendance. Anybody? Yasmin Jo Doroin, I think I said that correctly. Certificate of Accomplishment and Perfect Attendance. Anybody? Audrey Drews, Certificate of Accomplishment and Perfect Attendance. Gilbert? Nirek Duma, Certificate of Accomplishment and Perfect Attendance. Man's got the jammy swag coming on, I see it. I'm with it, my guy. I'm with it, my guy. Pictures? On you, bud.
Okay. Next we have Kevin Galea Solis, Certificate of Accomplishment and Perfect Attendance. Solis.
And this guy asked so many questions, they were great. Yeah, if you got a phone.
Christopher Georgiev, Certificate of Accomplishment. Christopher here.
Nope, I don't see him.
All right. Olivia Zamoranis, is that right? Certificate of Accomplishment and Perfect Attendance. Congratulations.
Zamoranis? Wow. Zamoranis? You want a picture or are you good?
Kevin Hadcock, certificate of accomplishment and perfect attendance.
Here you go, bud.
Victor Hansen, certificate of accomplishment and perfect attendance.
Victor, good to see you, bud. You want a picture? Yeah.
Logan Hayes, certificate of accomplishment and perfect attendance. Logan here.
Aw.
Max Huberty? Not sure how to pronounce that one. Huberty? No, Max? All right.
Hey, you're up front.
Okay.
Next, we have Layla Hubler. I want to see Layla. Certificate of accomplishment and perfect attendance. Dawood Hussein, certificate of accomplishment. Go. Sana Ershad, certificate of accomplishment. One? Okay. Uh-oh. Yusuf Islam, perfect attendance. I want to see it. Nirav Jain, certificate of accomplishment. Nirav is up there. Colin James, perfect attendance. Jack Johnson, certificate of accomplishment. You got next, buddy.
We're in the J's. Jackson Jones, perfect attendance. Nope. Victor Kaminsky, perfect attendance. Chithan Karandikar, certificate of accomplishment. Divij Kohli, certificate of accomplishment. Erika Komatsu, perfect attendance. Daran Koyilada, certificate of accomplishment. Elias Kutzner, perfect attendance.
All right. Mika Kutzner, perfect attendance. Emily Carudis, perfect attendance. Sarah Laus, perfect attendance. Henry Lewis, certificate of accomplishment. Nicholas Lyons, perfect attendance. Adil Mansouri, certificate of accomplishment. Oh, okay. Thought that was a student. Damian Marrero Roy, perfect attendance. Okay. And you, bud?
Okay. Anna Matevosyan. No? Maria Matevosyan. Perfect attendance. Madison Maxwell, certificate of accomplishment. Declan McCarthy, perfect attendance. Logan McCarthy, certificate of accomplishment. Caleb McLeod, certificate of accomplishment. Egan Meacham, perfect attendance.
Oh. Anna Miknicevic, perfect attendance. I'm sorry I butchered that. Go. Alessandra Menon, perfect attendance. One. David Mortulga, perfect attendance. Jesse, oh, sorry. Jesse Myers, Certificate of Accomplishment. Oh yeah, taking a pic. Where are we looking? Right there. Uh-huh. Rithika Nikanti, perfect attendance. Mithali Obidaje, Certificate of Accomplishment. Sean Pius, perfect attendance. Hey, bud, it's on you.
All right. Harper Papa Christos, perfect attendance. Kanak Parikh, Certificate of Accomplishment. Videep Sai Pita, Certificate of Accomplishment. Ayush Kumar Rai, perfect attendance. Idant Ranjan, perfect attendance. Nolan Rossier, perfect attendance. Matthew Romanovich, Certificate of Accomplishment.
Dabaria Saha, perfect attendance. Sanjar Salamov, Certificate of Accomplishment. Wait. Oh, this is strange. Please continue. We're good. Tamurbek Salamov, perfect attendance. Sayed Abdul Samad, perfect attendance. Okay. Melina Scherf, perfect attendance. Peyton Schultz, Certificate of Accomplishment. Kunj Shah, Certificate of Accomplishment. All right, but it's on you.
Right. Chang Shang, Certificate of Accomplishment. Ashman Sharma, Certificate of Accomplishment. Sanjit Sidhu, Certificate of Accomplishment. Ava Singh, Certificate of Accomplishment. Jackson Squires, Certificate of Accomplishment. Jason, sorry. Brain. Advita Srigopal, perfect attendance. Bhavishya Srivastava, perfect attendance.
Oh, I went the wrong way. Amara Sayeda, Certificate of Accomplishment. Arkit Tamhane, I hope I pronounced that correctly. Perfect attendance. David Taranowski, Certificate of Accomplishment. Dylan Thurlow, Certificate of Accomplishment. Rahul Tumidla, Certificate of Accomplishment. Oh, okay then. Hey. Good job, Burr. CB Vadivel, perfect attendance. Huh? Okay. Thank you. Evelyn Bang, Certificate of Accomplishment. Look at you.
The last slide, I presume. Ivana Verdon, Certificate of Accomplishment. Alyssa Westry, perfect attendance. Ethan Young, perfect attendance. Ernest Zhang, Certificate of Accomplishment. And that's all we have. That was me, I think.
Okay, everybody, so it's now time to be physicists, right? Congratulations, all of you. Everybody on Zoom, congratulations. Thanks for hanging out with us for the last 10 weeks, 11 weeks. Really hope you learned a lot. We hope that you got a lot out of this experience. Remember, we have internships. We have internships for people who are people who are in high school. We have official internships, and if you are sufficiently motivated, you can email a bunch of people, and if they have the room, they will take you on. It's happened a couple of times already. We also have internships for when you go to undergrad. Why? You can come here and you get paid. If you are so inclined and you still remember us, we also have internships for grad students, but we'll talk to you when you get to grad school. But that is, we have programs, if you are sufficiently interested, almost everything you've seen. You can work with people who are at the bleeding edge. So if you really like this program, if you really like working with us, come back, come hang out with us. You'll see more of the lab. All right.